So today what I would like to talk to you all about is how computers and humans think similarly and differently. And this is something that I'm going to approach sort of more from an engineering angle, not so much a philosophical angle. And that's because I'm a computer scientist. My background is in computer science. That's what I studied for my PhD, is computer science. So how, from an engineering perspective, is what computers, especially the new artificial intelligence, and humans, how are they similar and how are they different? So I'm going to begin with a brief overview of deep learning. And I'm going to do this because deep learning is the current state of the art. It's the best we've got in artificial intelligence research today. Alan Turing, a British computer scientist in the 1940s, said, "What we want is a machine that can learn from experience." And so entered machine learning, and then more specifically within machine learning, deep learning is the state of the art. It's important to note that throughout the history of artificial intelligence research, there have been two competing sort of, sometimes work together too as well, but two competing camps, schools of thought. One is based on this idea of machines self-adjusting, learning from experience, becoming better based on training data. And the other is based on the idea that humans, and we have intelligence, should take what we know and code it into the computer so it doesn't self-adjust, it doesn't learn from its own, but we just put what we know into the computer. They've sort of ebbed and flowed over time, which one has been dominant. For most of the history of artificial intelligence, the humans putting into the computer has been dominant, but recently deep learning has definitely been the dominant state-of-the-art research in artificial intelligence. So a brief history. In 1949, Donald Hebb, a neuropsychologist, wanted to crudely simulate, approximate on a computer what happened, what we understand about what happens in the animal brain. Now, what we understand about the animal brain is not everything, certainly, but we do understand some things. We understand that we have neurons in our biological neural network, and those neurons are connected by synapses. And so if one neuron, an electrical charge, fires through one neuron, if they're connected by a synapse, it's likely, it happens frequently, that the electrical charge will go through the synapse and the other neuron will fire as well. And it has been theorized that this is important to the learning process because Donald Hebb noted that neurons that fire together wire together. And what that means is that when one neuron fires, an electrical charge goes through the synapse so that the other neuron fires. Whenever that happens, it becomes more and more likely in the future for that to happen again. So it becomes more frequent. There's a sort of a feedback loop. And this seems to be, just like in learning, there's a feedback loop, right? When you connect two concepts, this sort of thing. So that was a simple approximation of what happens in the animal brain. This was improved upon in the 1960s. They had multi-layer perceptron models, is what they were called, which were a little bit more complex, a little bit superior to Hebbian models. And then there was a long dry spell in which that other school of artificial intelligence research really dominated, where the humans were coding in the knowledge into the computer. And one of the reasons for this is because of limited hardware. So the ideas for deep learning were there. The ideas of approximating what happens in the brain were there, but we didn't have the hardware to do it well yet. And that didn't come until the graphics processing unit became an important piece of hardware in the computer market. To explain the graphics processing unit, we have the central processing unit. The CPU, we're probably more familiar with, is the processor that's on every computer. Sometimes, and these can do complex tasks, but it can only do a few tasks at the same time. Sometimes, you might hear about a quad-core CPU or a dual-core CPU. That means that it can do 4 things at the same time, and a dual-core CPU can do 2 things at the same time. But a graphics processing unit, or a GPU, can do many things at the same time, 1,000 things at the same time, but very simple things. So the CPU can do complex things, but only a few at the same time. The GPU can do many additions or multiplications at the same time. And this is important because, for deep learning, this is important because when you're trying to simulate these connections between neurons in the brain, there are a lot of neurons and a lot of connections between neurons, and so you need to do a lot of simple operations, but you need to do them very quickly and very many times. And so in 2009, a research group used GPU hardware to train deep learning algorithm to classify images into different types, and this provided this was the hardware necessary for a breakthrough, and since then we've had a sort of renaissance in deep learning, and deep learning has been the state of the art in artificial intelligence research and has made strides beyond what we could have imagined before. So what is it that deep learning can do? Well, I talked about image classification, and that's one of the first tasks that deep learning algorithms did very well that previous algorithms, computer algorithms, could not do well. Here is a subset of the ImageNet dataset, which is a dataset of images that was used to train an artificial neural network, not a biological neural network, the one that's trying to imitate the biological neural network, to train an artificial neural network to classify images into cats, dogs, rabbits, airplanes, 2,000 different categories of types of images. They labeled 1.4 million images in order to do this well, and so that's a great many deal of images. And it surpassed all of the state of the art and is basically human level in performance at classifying images. Image generation is another interesting application of deep learning. All of the faces you see here are not real faces. However, especially the more recent ones are very convincing. And this most recent face is from 2018, and there have been 5 years of research since that. They're all fake faces that were generated by a deep neural network, an artificial deep neural network, to imitate a human face. And image generation has also been used to create new artwork in the style of various artists. This piece of artwork here is in the style of Van Gogh, for example. It's not a real Van Gogh, but it is a forged Van Gogh, maybe you could say. And also, not just images, but videos. Deep fakes have been used to create fake videos of people. This is not a video of Tom Cruise. This is a video of another person who, went through some motions, said various things, and put on the sunglasses. And then deep fakes was used to, without the help of any professional animators or anything of that sort, just puts Tom Cruise where the other person was and convincingly creates a video which is difficult to perceive as fake to the human eye, certainly. Self-driving cars is another application of deep learning that's maybe not quite there yet, but could be there and certainly has made significant strides. This has economic implications as many people are employed in the transportation industry. So it's important to consider those the consequences of self-driving cars as we move forward with this research. But again, that research really isn't quite there yet. We still need drivers behind the wheels of self-driving cars in order to intervene when the cars make mistakes. Board games is another application of deep learning algorithms where deep learning has surpassed humans and the generation of computers before. Chess, Garry Kasparov in the 1990s was defeated by a computer, Deep Blue, at chess using more traditional, the older generation of computer algorithms, computer artificial intelligence, based on the idea that humans are going to code their knowledge into the computer, and then computers are going to use their superior computational power to surpass human performance. But since then, deep learning-based chess algorithms have surpassed the previous generation of chess algorithms. So the best chess robots of today are based on deep learning and have trounced the previous generation of artificial intelligence algorithms, which was led by Stockfish, but AlphaZero, Google's chess algorithm, has defeated Stockfish handily. Go is a game that actually, until very recently, humans still outperformed computers. Until 2018, humans were outperforming computers, but in 2018, Google's team, again, created a deep learning-based algorithm, AlphaGo, to defeat the world's best Go players. Go is an Asian game with very simple rules, but very complex and very advanced strategy. Video games is another area where deep learning has proven impressive in its results. Dota 2 and StarCraft 2 are two examples of video games where deep learning has performed well. This StarCraft 2 player, actually, I think Mana, is a Polish player when I looked this up. So I think this is a professional StarCraft player who's playing against a computer opponent. Now, we're used to playing computer games against computer opponents, but for many of these strategy games, actually, these strategy games are very complex, more complex than board games. And when you're playing against a computer opponent, until recently, what they've done to make it challenging enough is they've given the computer opponent extra resources, extra advantages above the human, so that you as the human don't get bored defeating the computer opponent. But with AlphaStar team and the OpenAI's team that played Dota 2, which includes teamwork as well, that was not the case. It was no advantages for the computer, just a strong deep learning-based algorithm. And then we also have games with uncertainty, hidden information, like poker, and even games with negotiation, like diplomacy, where there's backstabbing, trust, you have to make agreements with other players. And all of these have had impressive results with deep learning-based algorithms. Another example is language translation. Here I have English and Polish. I don't know. I know English, but not Polish. But so maybe you can look at this and see if this is a good translation. But Google Translate is based on deep learning algorithms, and at least performs as well enough to be a good starting point, I think, for translation tasks. And this is an impressive result because language is something that is in many ways uniquely human. Which brings us to the last application of deep learning, which I think has been creating a lot of excitement on the internet, especially today, and that's large language models. Like ChatGPT is a large language model that is able to seemingly have a conversation with a person in a way that's, I think, very impressive. Here we have a question from a user: briefly explain ChatGPT using a metaphor that would resonate with an audience of stock market investors and avoiding artificial intelligence jargon. Well, this is a complex task, and in order to perform the task well, ChatGPT must first understand the complex task and then perform the task. In order to understand the task, it must understand things like metaphorical language. It must understand its audience, stock market investors, and it must understand what is jargon and what is not. It responds well. It says one way to explain ChatGPT to stock market investors is to compare it to a financial advisor who uses past performance data and market trends to make predictions about future investments. Just like a skilled financial advisor, ChatGPT uses large amounts of training data to generate intelligent and informed responses to questions, providing valuable insights and suggestions to users. And so this is, I think, a very good response to the question. Understood, it used a metaphor. It avoided artificial intelligence jargon, and it targeted its audience of stock market investors. So how does deep learning do all of these things? We've talked a little bit about what it does, but how does it do these things? Well, we'll start with image classification, which is the simplest task we discussed, and then we'll work our way up, sort of. For image classification, you have a artificial neural network of neurons and the connections, the synapses connecting them, the weights, we call them when we're working with artificial neural networks. And we use some of those neurons as the output. to determine what is in the image. Each of these output neurons will be either some number between 0 and 1 to represent a probability of that object being the object in the image. So you could be identifying here between apples, bears, candy, dog, and egg in the picture. So you input the picture, and then you have these output neurons between 0 and 1. Now, each of the images has actually been labeled by a human. And so a picture with a cat in it has been, the human has said, cat is in this picture. And so then the output neurons are compared with the truth. So if there is a bear in the image and the neural network has a 0 here, then the neural network is penalized, and in particular, according to that idea of neurons that fire together, wire together, the neurons connected, the weights connected with this neuron that were responsible for the incorrect prediction are penalized most. And so blame is assigned to neurons according to whether it got the correct result or incorrect result. And similarly, if it gets the answer correct, not blame, but credit is rewarded to neurons according to which ones were responsible, if you will, for getting the correct result. And that's how the neural networks are trained. So that's image classification. What about image generation? Well, many of the same ideas still apply, the idea of credit and blame and this sort of thing. But the process is a little bit different. For image generation, you actually train 2 neural networks. And you can think of them as sort of playing a game. You've got an art forger and an art expert. The generator is the art forger, and the discriminator is the art expert, trying to look at the 2 Leonardo da Vincis and see which one is the real Da Vinci and which one is the fake. The generator creates a fake image, in this case, let's say a face, and then the discriminator is given a fake face generated by the generator and a real face that from a collected data set. The discriminator has to then decide which face is real and which one is fake. It's the art expert. If the discriminator performs its tasks well and guesses correctly which image is real and which is fake, then it is rewarded, and its neurons are rewarded according to their responsibility. If it guesses incorrectly, it is penalized. On the flip side, the generator, if the discriminator guesses correctly, then the generator has not created a convincing enough forgery, a convincing enough face. And so it is penalized if the discriminator guesses correctly, and it is rewarded if the discriminator guesses incorrectly. And so that's 2 neural networks in order to create a generative neural network, to create fake images. What about language models? Well, language models are the most complex models to train. And this, I think, makes sense given that language is very complex. So it's trained in different phases. The first phase of training a language model is pre-training, unsupervised. You don't need a human labeling what's a cat or a dog or anything like that. You just take text from the internet. You can think of the neural network as reading the internet or reading all the books that are out there. It's going to go through text, and it's going to have words blanked out randomly. And it's going to have to predict what word fills in the blank using the surrounding words. So here we have the cat sat on the mat might be the first prediction, but there are many answers that could fill in this blank. The cat sat on the chair. The cat sat on the couch. The cat sat on the rock. All of these are acceptable answers. And so the language model has to learn grammar. What words are nouns, verbs, what words work where. But it also has to learn something about the relations between words. For example, the blank empire was ruled by Julius Caesar. In order to correctly fill in this blank, the neural network must relate Julius Caesar to Rome. And so it has to learn to relate words to each other in ways that are meaningful. A cheetah is a spotted animal. It's a fast animal. This is a relation between 2 different words. So that's the first step in training a large language model like ChatGPT. But then there is another step. Just like the generative neural network, where you had an art forger and an art expert, you're actually then going to split this model, which by now should have some idea of grammar and some idea of relations of words. You're going to split this model into two, and you're going to have one model, which is going to be called the reward model, and the other, which is going to be the final product, ChatGPT itself. You're going to train the reward neural network according to human-based, now you're going to have labeling, human labeling. Humans are going to be given a set of questions and a set of answers to those questions. And the human labelers will rank the answers according to how well, which answer they think is best, which they think is worst, from best to worst. The reward neural network will be trained to imitate the human preferences of the labelers. And then the reward neural network will be used to train ChatGPT itself, so that ChatGPT can be given a set of questions, will generate multiple different answers, and the reward neural network will rank those answers imitating human preference, the human labeler's preference. And in this way, ChatGPT will learn to satisfy human preferences in its response. One important thing to note here is that whoever controls the labeling process, whoever ranks the answer, has a significant impact on the large language model's biases. This could include political biases, amongst other biases. And so it's important to think about that. It's important to note that, if you've got people of different political persuasions labeling, ranking answers, then that bias might come through, and at the reward model will be biased similarly to the humans who were biased, and then ChatGPT may also be biased as a result. So why is deep learning different? It seems that deep learning can do many things similarly, many of the same things that humans can do that computers could not do before. So why is computer thinking different from human thinking? Well, in a couple different ways, some small and some big. Deep learning has some advantages over humans, certainly. For example, computers are tireless. We've all had the experience studying for an exam or working on a project, and we get tired, right? And what do we have to do? We have to sleep. We can't keep on working if we're too tired, or we can't keep on working at the same effectiveness at least. And so we have to go to sleep, wake up in the morning, and finish our work again and start working again. But computers, you plug them into the wall, and they will keep on working. And so that's an advantage they have over us. Computers are also more flexible in the inputs and outputs. Inputs you can give them and the outputs you can ask them to produce. For example, as humans, we have the 5 senses, right? We have sight, hearing, we have touch, taste, and smell. And we live in a 3-dimensional world, so we're able to process 3-dimensional data. So we're able to process things according to our experience of the world, which is through the 5 senses. But a computer, you could give a computer all sorts of different sensors to work with. You could give it, for example, a self-driving car. You don't need to give it 2 eyes. You can give it 12 different cameras all over the car. And you can have it learn how to use all of those cameras together to drive well. And so that's an advantage computers have over us, because we can't really process data like that. Computers can learn to process data in different dimensions than we can. So computers are in some ways more flexible, but in other ways we'll discuss about soon, computers are less flexible. You also have data requirements, and so this is actually a disadvantage of computers. Computers require much more data to learn than humans. I mentioned that first example for image classification, 1.4 million images. If you had to look through 1.4 million images to learn the difference between dogs, cats, rabbits, and airplanes, you would still be studying, and you would certainly not, for probably most of your life, if not all of your life, before you would finally know the differences between these different things. Deep learning requires lots of data, and frequently it requires a lot of labeled data, which can actually be expensive. To give you an example, some of you may have already known what a gibbon is, but I didn't know what a gibbon was, so I included this in the talk. Here we have a gibbon. So I've given you one picture of a gibbon. And if I gave you another picture of a gibbon in a different posture, in a different background, different setting, you could probably pick out the gibbon pretty well, right? You've learned very quickly. From one picture of a gibbon, you have some idea of what a gibbon is, a pretty good idea of what a gibbon is. But computers need lots of data, like 1.4 million images. And because of this, one of the things that deep learning engineers, we do as deep learning engineers, is we try to make our data sets bigger, because computers learn better if you give them more data. Here I have a picture of a duck. Well, that's one picture of a duck. But how can I make it into more pictures of a duck so that the computer can learn better? Well, I can take the mirror image of the duck, and now I have two ducks. I can rotate the duck, and now I have already as many ducks as I want. I can zoom into the duck and crop the duck in various ways. I can change the color scheme, blur the duck, use different contrast, and add randomness to the duck, or speckle the duck. All of these things help the computer learn from less data. It creates more data from less, and that's very useful for the computer. However, if you're trying to teach your kid what a duck is, this is not going to be particularly helpful, right? If you create all these new images of the same duck, just slightly different, cropped, tilted, different ways, that's not really going to help the kid learn what a duck is. So clearly there's something different between how the computer is learning and how the human is learning. Another thing done to make data sets bigger is to block out part of the images. I just wanted to give this as another example because really data augmentation, it's called, making the data set bigger, is very important to deep learning. So I'm going to suggest to you that this illustrates an important difference of computers' inability, current inability at least, to think outside of the box. Computers think inside the box, I will argue, and as humans we think inside the box, but we can also think outside of the box. And what does this mean? Well, here I have a picture of a curve. If you're trying to learn what the points on the curve are, and you can only interpolate or find points in between other points to estimate the curve, and I give you these two gray points, you will probably guess the red point, and that would be a good guess for the third point on the curve. But really, the curve is as shown, and the green point is the correct curve. So what's the solution? If this is your only way of learning the curve, you need more points on the curve in order to learn what the curve is. And so here we have the curve again, a slightly different curve, and we have one curve densely sampled and one curve sparsely sampled, just a few different samples from the curve. And we see that with the densely sampled, learning in between, you can learn in between the gaps and you can learn what the curve is. But with the sparsely sampled case, you cannot. Even we could not for this particular task. But humans can think outside of the box where computers cannot. And all of that was preparing you to give you an intuition of what I mean by that. Here I have gray parallelograms on the right. If I give these gray parallelograms to a computer to train on, and then I give it the green parallelogram, which is not identical to any of the gray parallelograms, but is sort of intuitively, I think we can agree, in between or inside of the experience of the gray parallelograms, the computer will likely perform quite well. The red parallelogram, on the other case, is quite dissimilar to the gray parallelograms, and so the computer is much less likely to perform well. Although for a task this simple, it still may be able to perform this task. But this is to illustrate the concept of thinking inside the box versus outside the box. On the other hand, we as humans who know that a parallelogram is a four-sided figure with two sets of parallel sides, both the green parallelogram and the red parallelogram, we will perform quite well. This is also important for things like learning how to identify stop signs. You want the stop signs at all the different angles so that the computer can learn to identify stop signs at all sorts of different angles. Another difference is that computers and humans are tricked differently. Certainly you can trick a human, and certainly you can trick a computer, but the way in which you trick them does not always look alike. Here we have two pictures of pandas, except one picture, this picture on the right side of the screen, has been slightly modified, strategically modified, to trick a particular neural network into thinking that it is not a panda. And so the neural network has predicted that this is a gibbon with 99.3% confidence. The original confidence for the original image was 57.7% confidence that the original image was a panda. We cannot even tell that these two images are different. The difference is so slight. And yet the computer has been tricked to be quite confident that this is a gibbon. As a reminder of what a gibbon is, in case you didn't learn from the first example, although this is the same example, that is what a gibbon looks like. So there's a significant difference, right, between the panda and the gibbon. Here's a real life, maybe a little bit more of a scary example, adversarial example. Here we have two stop signs, and one stop sign has been modified, paint has been put on it to convince the computer that it is not a stop sign, and the computer has incorrectly identified this stop sign as a sports ball. This could be concerning if you're buying a new self-driving car, right? You don't want your self-driving car to think that this stop sign is a sports ball, because then it will not stop at the stop sign, and that could be dangerous. But what about state-of-the-art large language models like ChatGPT? It seems that this is, and I think this is, I would say, the most similar thing that we have of artificial intelligence. And so how is it different? Can it think outside of the box? Or does it also think inside of the box? Are there any other differences? We'll discuss that it can both, I will argue that it can think only inside the box, and I will give you some examples to illustrate that. And I also argue that there's another difference, that ChatGPT not only can only think inside the box, but it really only has access to symbols, words, symbolic manipulations of words. Greek philosopher Aristotle says that spoken words are symbols of mental experience or ideas, and written words are symbols of spoken words. Just as all men have not the same writing, so all men have not the same speech sounds. For example, you've got English and Polish. But the mental experiences, which these directly symbolize, are the same for all, as also are the things of which our experiences are the images. And from this, we get the semantic triangle, as it is called. We have the word, the symbol, which refers to an idea in our mind, and then we have the thing in reality. The idea corresponds to the thing in reality. So word, idea, and thing. And we as humans have access to all of these. But the computer, I will argue, has access only to the symbols, only to the words. It doesn't have understanding of meanings in the ideas. Okay, so computers have been good at working with symbols, working with words and symbols in some ways, for a long time. Here we have 2 + 3 = 5. Those are symbols, right? And computers have been very good at arithmetic since the beginning of computers. That's what they do best, right? They're much better at humans at manipulating these symbols. We have algebra. Computers are also very good at algebra and have been for quite some time now. Search and replace, which is very useful, right? If you're writing your paper and you misspelled a word everywhere, right? Computers can manipulate symbols in this way. And these are words, not just math, right? And all computer code. There's a reason we call computer languages like Python and Java languages, because there are similarities, right? There are symbols, there are words in these languages, Python and Java, for example. But all of these are precise symbolic manipulations. Computers have been very good at precise symbolic manipulations using what are called context-free grammars for quite some time now. But until recently, with large language models and deep learning and models like ChatGPT, computers have struggled with human language, because human language has not so much precision, but ambiguity and fuzziness. Computers have only the symbols, not the underlying ideas, and again, until recently, have struggled with human language's fuzziness. What is human language's fuzziness? Well, here's an example. He looked at the dog with one eye. This is an ambiguous sentence. It can have different meanings, right? You need context to know what it means. We as humans need context to know what it means. He looked at the dog with one eye can mean he looked at the dog using only one of his eyes. Or he looked at the dog with one eye can mean that he looked at the dog with both of his eyes, but the dog he was looking at had only one eye. Computers struggle with this sort of fuzziness, although not so much anymore. Okay, so I've made two claims, and I'm going to give you examples to back up those claims. What are the two claims? That computers, even large language models like ChatGPT, can think inside of the box, but they cannot think outside of the box. And the second claim is that large language models like ChatGPT are only manipulating symbols. They don't have underlying ideas, they don't have consciousness or anything of the sort. They can only manipulate symbols. Brief disclaimer. I mentioned when we talked about the training of large language models like ChatGPT, there are two steps. There's a pre-training step, and then you train the reward model and ChatGPT together. The pre-training step is very expensive, costs millions and millions of dollars in just power costs alone. You think about plugging a computer into the wall, right? That costs some power to run it. They're plugging servers into the wall, and it takes time to train this neural network, and it takes power consumption. So it's very expensive, so they don't do it very often. In fact, they did it sometime in 2022, and so it's not completely up to date. Things like Pope Benedict or Queen Victoria, it thinks both of them are still alive, for example. However, the last stage in the training process doesn't take so long. Training the reward model, retraining the reward model, updating the reward model, and ChatGPT itself. And so they update it reasonably frequently, and you'll get different responses day to day. And it's actually improving, notably. I've noticed that it is improving. And so just because I give you the examples here today doesn't mean that ChatGPT will always be tricked in this way. However, I hope to show you how to trick ChatGPT yourself so that you have the ideas, you have the understanding, so that you can go to ChatGPT and figure out ways to trick it yourself if you enjoy doing that sort of thing. Okay, so what are some ChatGPT examples? So here I give it, if 5 ampersand, that's the ampersand symbol, if 5 ampersand 5 is 10 and 7 ampersand 9 is 16, what is your best guess for 3 ampersand 8? So here we have the ampersand symbol being used where normally we would use the addition symbol, right? We have an idea of addition, and we're familiar with the symbol that's used for addition, the plus sign. And so we would say 3 ampersand 8, well 3 plus 8, 3 added to 8 is 11, is the correct answer. And we can do this quite easily because we have an idea of addition. And so we're able to remap this symbol that we're not familiar with being used in this way, but we're able to quickly remap it to a concept that we already have. We're able to flexibly adjust. ChatGPT, it is not the case. ChatGPT thinks that 3 ampersand 8 is most likely 0, not 11. Now the reason it thinks this is because the ampersand symbol is frequently used as the bitwise AND operator, which is a computer operator. And so it's not able to adjust and see that it is not being used in this way here. Again, because it doesn't have the underlying idea of addition like we do. It just has the symbols, and it's used to the symbol ampersand being used in just one way. Another example, Progo is a nickname I personally use. So Progo is a made-up word. Progo is a nickname I personally use for a famous historical figure who ruled Rome before he was assassinated by his friend. If you absolutely had to guess, who would be your first guess for who Progo might be? I intended, and I think it was a reasonable intention, for it ChatGPT to answer Julius Caesar. ChatGPT instead dodged the question. And I tried to ask the question multiple different times, trying to force it to answer. You see here, I tried to force it to answer with the if you had to absolutely guess, because sometimes that does work. I have successfully got it to answer questions by trying to force it to guess in that way. But here, it dodged the question. It said, I don't have enough information. And so it was unwilling to make a guess as to who Progo might be. Because, again, this is an example of remapping a symbol, Progo in this case, remapping a symbol to an idea that we have, right? A new symbol, but the same idea for us, but for the computer, a new symbol, no underlying idea. Here I give it a few more tasks. I ask it to list 3 valid English words containing only the first 5 letters of the alphabet and not containing any of the other letters. Not a terribly difficult task. 3 examples would be bad, cab, and ace. It gives some very advanced words. I actually don't know what all these words mean, but I will assume that they're valid. I do think these are valid words, but they do not. They use letters outside of the first 5 letters of the alphabet. Indicating that ChatGPT failed to understand the initial question in this case. Replace everything between the X and Z with A in the following, and then I give it a string of characters. So I'm trying to test if its understanding of words like replace and between. From its answer is incorrect. It should be answering right here. But instead it answers right here. It does seem to have a concept of replace, or not a concept, but it seems to have the relations of words with respect to replace. It seems to have performed a part of the task, but it has eliminated the X and the Z and has not replaced all these characters with A. So ultimately, it was missing something, maybe between or something like that. It doesn't have a grasp of the ideas. Here's another example. I gave it this example. I was actually trying to trick it in a different way, and then I got more than I expected. I tricked it more than I expected I would. If you subtract a multiple of 7 from another multiple of 7 more than 3 times the size, will the result be a multiple of 7? Will it be prime? So it gives a rather long answer, which it sometimes does. But I'm going to point you to the highlighted section here. It says you get 28. Which is a multiple of 7 and also a prime number. Well, if you're adding multiples of 7 together, right, you will get a multiple of 7. And you also, if you're subtracting from a number 3 times the size, you will not get a prime ever. Well, 28 is not a prime number, right? It has factors 1, 2, 2, 7, and it has the prime factors 2, 2, and 7. And so it incorrectly thinks here. It incorrectly states that 28 is a prime number. But because I know how ChatGPT works, I know how these algorithms work to a certain extent, I knew that if you give it the question in the right way, inside the box, with what it's familiar to, in a simple way, it should be able to answer this correctly. And so I ask, is 28 a prime number? And it says, no, 28 is not a prime number. It is divisible by 1, 2, 4, 7, 14, and 28. And that's because this phrase is phrased in a very simple way, in a very familiar way, in a very simple and familiar way with which ChatGPT can work well. So Francois Chalette is a French artificial intelligence researcher, very significant in the field. He's a major contributor to the PyTorch and Keras deep learning libraries. Two of the 3 libraries used most by artificial intelligence researchers across the world. And so he's a major figure in the field. And he says the gap between generating words, or the symbols, and generating meaning, the ideas, will prove hard to close. Generating meaning requires a model of the things being talked about, language as communication. While generating words only requires a model of the structure of text, language as statistics. And I'm not the only one who enjoys sometimes trying to play with ChatGPT a little bit. Francois Chalette gives some demonstrations as well of various ways to trick ChatGPT. he gives it some simple reasoning tests. He gives it examples, and from those examples it has to catch the pattern and correctly apply the pattern to a new example. Here in this example, the first and last letters should be capitalized. ChatGPT fails at this test and instead alternates capital and lowercase. Another example he gives, here you're supposed to replace what's outside of the X's with O and what's inside of the X's with A. ChatGPT does identify that it should have just O's, X's, and A's, but it creates more X's than it should and ultimately fails to perform the task. And Francois Chalette says, this is all very low complexity. These are simple tasks. But that's irrelevant to a large language model's ability to handle the tasks. Only familiarity matters. As long as you're dealing with a variation on something the model has seen before, something inside the box, you're good. But whenever some novelty arises, the model can't reason on its own. And so in conclusion, I'll make two claims. Deep learning can imitate many human behaviors, but only using interpolation, thinking inside of the box, inside of the data it has been given. But it cannot extrapolate or reason well to something new or original or novel like we can. Furthermore, ChatGPT can masterfully sequence symbols or words, all without having any understanding or ideas of the symbol, what the symbols represent, the concepts that the language represents. And so that is my talk on how humans and computers think both similarly and differently. I hope you've learned something today, and please, if you have any questions, let me know, and I'd be happy to answer any questions on the talk. Thank you.